Vector joining 2 points. Welcome, everyone. Today, we are moving into a very important topic, vector joining 2 points. Now, in our previous lessons, we focused primarily on the position vector of a single point, specifically looking at how that point relates back to the origin, which we denote as capital O. That was a great foundation, but it only tells us where a point is located relative to a fixed starting point. However, in the real world, whether you are calculating the path of a drone or the movement of a particle, we often encounter scenarios where we aren't interested in the origin at all. Instead, we need to find a vector that connects two arbitrary points anywhere in space, where neither of those points is necessarily the origin. In this tutorial, I will guide you through the step-by-step process of how to determine the specific vector that joins these 2 points, and more importantly, I will show you how to calculate the magnitude or the actual distance between them. Let's get started. Understanding the concept. Imagine we are working within a 3-dimensional coordinate system, and we have 2 arbitrary points. Let's call them P1 and P2. As we discussed in the previous slide, we already know how to describe these points using position vectors. So, the position vector of P1, relative to our origin O, is represented as vector OP1. Similarly, the position vector of P2, relative to the origin O, is vector OP2. But our goal today isn't just to locate these points, it's to find the vector P1, P2. This specific vector represents the displacement, or the direct path, moving from point P1 to point P2. To understand how to calculate this, we can use the triangle law of vector addition. Think of it as a journey. If you start at the origin O, travel along vector OP1 to reach point P1, and then immediately travel along vector P1, P2 to reach point P2, you have essentially completed a single trip from the origin directly to P2. Mathematically, we write this sequence as vector OP1 plus vector P1, P2 equals vector OP2. Now, since our objective is to find that connecting vector, P1, P2, we can use simple algebra to rearrange this equation. By subtracting vector OP1 from both sides, we isolate our target. This gives us the formula. Vector P1, P2 equals vector OP2 minus vector OP1. To put this in simple terms that you can always rely on, the vector joining any 2 points is always found by taking the position vector of your terminal point, that's your destination or the end, and subtracting the position vector of your initial point, which is your starting point. Now that we've established that we are moving beyond just looking at points relative to the origin, let's dive into the core concept of how to connect any 2 points. In the next slide, we will take this conceptual idea and translate it into a concrete algebraic formula using x, y, and z coordinates. Algebraic representation in component form. First, let's define our points. Suppose we have 2 points in 3D space, point P1 with coordinates x1, y1, and z1, and point P2 with coordinates x2, y2, and z2. Step 1, we need to write out the position vectors for these points. As we discussed earlier, these vectors start from the origin. So, the position vector of P1, which we call OP1, is expressed in terms of its components as x1i plus y1j plus z1k. Similarly, the position vector of P2, or OP2, is x2i plus y2j plus z2k. Step 2, this is the most important part. We subtract the initial position vector from the terminal position vector. Using our notation, the vector P1, P2 equals OP2 minus OP1. In terms of our components, this means we take the vector x2, I plus y2j plus z2k, and subtract the entire vector x1i plus y1j plus z1k. Step 3, finally we group the components together. We subtract the x components, the y components, and the z components separately. This leaves us with a very clean final formula. The vector P1, P2 is equal to the quantity x2 minus x1, all for the I component, plus the quantity y2 minus y1 for the j component, and finally the quantity z2 minus z1 for the k component. Now that we understand the conceptual idea of subtracting position vectors from the previous slide, Let's look at how we actually perform this calculation using algebra. To solve this, we follow a simple three-step process. This formula is incredibly useful because it gives us the exact direction and magnitude of the vector, which we will use to calculate the actual distance in the next slide. Magnitude of the vector joining 2 points. The magnitude of the vector, which we denote as P1, P2 with vertical bars around it, represents the actual physical distance between our 2 points, P1 and P2. Think of it as the straight line length of the arrow we just calculated. To find this, we use the magnitude formula for a vector in component form. As you can see on the slide, the magnitude of P1, P2 is equal to the square root of the quantity, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Now that we have successfully found the components of our vector in the previous slide, we need to address one more important question. How long is this vector? Essentially, we are taking the difference in each dimension, squaring them to ensure we have positive values, summing them up, and then taking the square root to return to the original scale. We will apply this exact process in the next slide when we look at the drone navigation example. Real-world example, drone navigation. Imagine a scenario involving a delivery drone. Currently, the drone is positioned at point A with coordinates 2, 3, and 5 meters. It needs to fly to a specific delivery location at point B, which is located at 5, -1, and 10 meters. Our objective is to determine two things: the displacement vector of the drone and the total distance it must travel. To solve this, we will follow a clear step-by-step process. Step 1, we must identify our coordinates. As we discussed in the earlier slides, it is vital to distinguish between our starting point and our destination. Here, point A is our initial point, so our x1, y1, and z1 are 2, 3, and 5, respectively. Point B is our terminal point, meaning our x2, y2, and z2 are 5, -1, and 10. Step 2, we will find the displacement vector, which we denote as vector AB using the subtraction formula we learned in slide 3. We subtract the initial components from the terminal components. This means we take the x2 minus x1, all in terms of the I component, plus the y2 minus y1, in terms of the j component, plus the z2 minus z1, in terms of the k component. Plugging in our values, we get 5 minus 2 for the I component, -1 minus 3 for the j component, and 10 minus 5 for the k component. When we simplify these subtractions, we arrive at our displacement vector, 3i minus 4j plus 5k. Step 3, now we need to calculate the total distance, which is the magnitude of our vector AB. Referring back to the magnitude formula from slide 4, we take the square root of the sum of the squares of our components. So, we calculate the square root of 3 squared plus -4 squared plus 5 squared. Squaring these numbers gives us 9 plus 16 plus 25. Adding these together, we get the square root of 50. We can simplify the square root of 50 to 5 root 2, which is approximately 7.07 meters. So, the drone's displacement is 3i minus 4j plus 5k, and the total distance traveled is approximately 7.07 meters. In the next slide, we will wrap up this tutorial by reviewing the key takeaways you should remember. Now that we have covered the theoretical foundation and the algebraic formulas in the previous slides, let's put everything into practice with a real-world application. Key takeaways. First, let's revisit the fundamental formula. To find the vector joining point P1 to point P2, you simply take the position vector of the endpoint and subtract the position vector of the starting point. In mathematical terms, that is, the vector P1, P2 equals the vector OP2 minus the vector OP1. Now, I cannot stress this enough: direction matters. When you are performing this calculation, the order of subtraction is absolutely critical. You must always subtract the initial point from the terminal point. If you swap them, you'll end up with a vector pointing in the exact opposite direction. If we look at this in terms of its algebraic components, as we saw in our earlier slides, the vector p1, p2 can be written as x2 minus x1 times I plus y2 minus y1 times j plus z2 minus z1 times k. This component form is what allows us to work with these vectors in a three-dimensional coordinate system. Finally, remember that the magnitude of this resulting vector represents the actual Euclidean distance between the 2 points in three-dimensional space. It's the straight line length between them. All right, let's wrap up what we've learned today by reviewing the key takeaways from this lesson. Before we move on to the final slide, where I'll highlight some common pitfalls to watch out for in your exams, I want you to ensure you are comfortable with this head minus tail concept. Common mistakes to avoid. Now, as we wrap up this tutorial, I want to pause and highlight some common pitfalls. Even if you understand the concept of joining 2 points, these 3 mistakes can easily lead to incorrect answers in your exams. First, let's talk about the incorrect order of subtraction. This is perhaps the most frequent error I see. When you are asked to find the vector from point P1 to point P2, some students accidentally calculate the position vector of P1 minus the position vector of P2. If you do this, you'll end up with a vector that points in the exact opposite direction of where you intended to go. To keep yourself on track, always use the mnemonic, head minus tail. You are subtracting the starting point from the ending point. Second, watch out for sign errors. This isn't strictly a vector problem, but it's a classic algebra trap. When you are subtracting coordinates that are already negative, you must be very careful with your signs. For instance, if the x-coordinate of your first point is -2 and the x-coordinate of your second point is 5, the calculation must be 5 minus -2, which simplifies to 5 plus 2, giving you 7. Many students mistakenly just subtract the absolute value and get 3, which is incorrect. Always use parentheses to keep your signs clear. Finally, do not confuse the vector itself with its magnitude. It is vital to remember the distinction between the two. The notation P1, P2, with the arrow on top, represents a vector, which is a quantity that contains both magnitude and direction. On the other hand, the notation with vertical bars around P1, P2 represents the magnitude, which is a scalar value. This is just a single number representing the distance, and it has no direction. Keeping this distinction clear will help you avoid confusion when solving more complex problems in the future. That concludes our lesson for today. Keep practicing, and I will see you in the next tutorial.